Okay, so for here, I'm just going to go through some notation that people use when working with functions. I mean, you probably noticed already that little f tends to be used for functions, but other notation people use are G, H, capital F, capital G, and capital H I've seen to denote functions. Generally from the content, it will be clear. For the most part, little f or little g is what people will use to denote a function. Also, little x will represent something from the domain. So basically an arbitrary input. And remember how a function, the domain is denoted by capital X. Little f, if f is a function, little f is mapping elements little x into a set capital Y. Generally, to denote something in capital Y, they use lowercase y. The element that f maps x to is denoted by f of x. So if x is your input, you could think of the function as giving you back output f of x. And really, to just denote that this is what's happening, people generally will write this. So if you see y equals f of x, which you will see when working with functions, in the background you have some set capital X, which is your domain. Capital Y is the set the range lives in. Little x is represents your arbitrary input. The element in y you get back is f of x. So again, it's just fancy notation. What some people also say in this case is they say x is an independent variable, and since y depends on x, y is the dependent variable. Also, if we went back to this relation stuff, capital X would denote the collection of all our first components or our x coordinates. Capital Y would be the collection containing the second components. I mean, for the most part, Y was the set of all second components. Also, when you have a relation that is a function, each ordered pair you could think of as being like this, x comma f of x. Okay. Now what we're going to do is consider graphs of functions. We can actually graph any relation because remember, a graph is really just a collection of points that are plotted in the plane, as we have seen earlier. So from every relation, you can get a graph. And really, from any graph, you can actually get a relation. I mean, the relation, there might be infinitely many points, but it's still a relation. Not every graph, though, gives us a function, just like not every relation gives us a function. And how do we tell which graphs are graphs of functions? Well, that's where this vertical line test comes into play. Basically, if you have a graph in the plane, it is the graph of a function, or you can think of it as defining a function exactly when no vertical line intersects the graph more than once. Another way of saying that is every vertical line will intersect the graph either not at all or once, at most once. And again, when a graph does pass the vertical line test, it does define a function because every point you could think of as looking like this, where f is the function, of course. So in particular, any line that's not vertical is the graph of a function. We know it's the graph of something of this form. So we can use that to define a function. Something that would not be a function would be something like a circle. You know, something like this. This fails the vertical line test. I mean, it's easy to see that, right? As you can see here. That does not pass the vertical line test. Let me just put x and y in here, okay? Or as another example, something like this would also fail the vertical line test. So these are graphs. They're not graphs of functions. Okay, good. Okay, so now you might be wondering, why does the vertical line test work? Well, remember, every vertical line has equation x equal to a, right? X equal to a for some number a. So if that were to intersect the graph, let's say you had a graph, right? And let's say you had a vertical line, x equal to a. Well, that vertical line is going to intersect the graph at some point of the form a comma b. I don't know what b is, but if this was the graph of a function, well then f of that a, if f is the function, f would have to send a to b. Okay, but what if it intersected the graph more than once? Let's say you had something like this. So let's say now you had a vertical line, it's intersecting the graph twice. Okay, so again, this is going to be a, we'll call this C. This will be a comma b. So it's intersecting the graph twice. So now you have 2 points. They're not equal. Their x coordinates are the same. Well, it's just like a relation. You can't have that if it's going to be a function. Again, what's going to happen is, well, then f of a would have to be b, but f of a would also have to be c. Well, unless b is equal to c, which is not the case here, that function is sending a to 2 different outputs, which in a function cannot happen. Okay, now the graph is actually very useful. You can learn a lot about a function from the graph. It can be a little tricky to know what the domain and the range are, but basically the domain is the portion of the x-axis that's either above or below the graph. And essentially you can project the graph onto the x-axis in order to determine what the domain is. So let's say you had something like this. Okay. Now, what would the domain be? Well, again, that's the portion of the graph. Excuse me, that's the portion of the x-axis that's either above or below, in this case below, the graph. So it would be everything here. That's what the domain is. That's the part, that's where all the inputs are for the function. And for the range, the idea is similar. Let me use a different color. The only difference is you're going to project onto the y-axis. So in this case, you're going to move left to right. So right to left in this case. You would project. So in this case, you're going to have, for the range, all this. It's where all the y coordinates live.